think it doesn't work.
Select red? No, you don't do it. As long as the light is red. Is it on?
It's on?
The light is red?
Yeah, now it's on. Okay. So let me thank the organizers for the invitation. I would like to make some comments in this talk on realizations of mass hierarchies in string theory. So before that, let me I'd like to make a few more general comments. This is a string phenomenology conference, and of course one of the main topic is how and if and how string theory is connected to the real world. I would agree with a statement of Bob Acharya's talk in the first day, that string theory is a framework that can provide that can have several realizations, and in particular can provide models of particle physics. It could also be just a tool that could describe other physical systems that have been a lot of work during the recent years, for instance using ADS-CFT that could provide tools to study even QCD or statistical mechanical systems. Now going back to particle physics, I think one of the distinctions that one should make is a distinction between string theory, real string theory, let's say constructions and predictions, and effective field theory. I mean, it is true that string theory, in the string framework, one could accommodate many particle physics models using effective field theory, but in my opinion, should not confuse what predictions mean as predictions of effective field theory, or predictions that go really that one can make only if string theory is there. I think that's very, very difficult to and very few examples that you can imagine. And the other comment is concerning the string landscape, which again, to me, a string landscape, although it has 10 to the 500 vacua, is just a small corner of the full space of vacua of string theory. That if you are allowed to, for instance, to include vacua, which we know that are stable and we have flat directions and many supersymmetries and can live in even higher dimensions, for instance in 10 dimensions, then the landscape of 10 to the 10 to the 500 vacua is just a measure zero compared to the full space of string vacua. So okay, all this I think is things that one should take into account. And what I find more important is to use string theory as a framework in order to find perhaps new realizations and new models of new ideas for particle physics, which happened during the last years. So okay, having said this, so I go back to this work. So that is the outline. And since my initial point is the let's see how this works. It's the hierarchy problem. I want to start with low energy supersymmetry, which provides the standard and picture that most of us believe or like more, let's say, which has several advantages. From introducing elementary scalars, providing a framework for gauge coupling unification, having a dark matter candidate, giving a way to have radiative electroweak symmetry breaking. And on the other hand, of course, we have the problems that we know. One is related to the mechanism of supersymmetry breaking, which provides many the zoo of the soft terms. And the other, the experimental situation, which for the moment becomes worse and worse from the point of view of fine-tuning supersymmetry, at least in its minimal version, the MSSM. And to my view, this the natural framework from the string theory point of view that can accommodate this possibility is the heterotic string. In a perturbative or in not perturbative version, in the sense that in this theory, unification is natural. If we go to intersecting branes, it is true and can discuss of models. However, the unification becomes unnatural, and I don't already taken out the unification from the consequence of from supersymmetry. For me, it's okay. Already loses some of part of the motivation, of main motivation. On the other hand, okay, let me say a few words, personal comments about the Higgs search, which seems to be already from last year, but seems also to be confirmed this year, that there is an excess of Higgs-like in the light mass region. This is consistent with the expectation that we had from precision tests of the standard model on one hand, and on the other hand, from the theory point of view, it favors perturbative physics, that's clear. On the other hand, if its mass is confirmed to be around 125 GeV, which is an interesting region, in this region, supersymmetry, although supersymmetry can accommodate this Higgs, it becomes severely, depends how, at least in its minimal version, fine-tuned. But on the other hand, it's interesting because on the other hand, one cannot draw a general conclusion before waiting for the results of the next round of LHC, which will have double energy. And we know already that, for instance, abandoning the minimal version, introducing additional singlet or split families, one can remediate the fine-tuning to reasonable values. The final point, which is very important, is to be able to measure Higgs couplings, because any deviation of the couplings of the Higgs to, for instance, the top-bottom electroweak gauge bosons implies that there are new states, new light states, that are involved in the electroweak symmetry breaking, and of course these states can alter the arguments of the fine-tuning. What I will talk mostly is an alternative, the alternative answer to supersymmetry, since for the moment we can still, it is an allowed possibility, which is by introducing, by having a low string cutoff, a low ultraviolet cutoff, which in the effective field theory, for instance, can be realized in models of low-scale gravity, or in the case of string theory directly, by lowering the string scale. I mean, one important point is that in such a framework there is no little hierarchy problem, in the sense that the electroweak symmetry breaking can be occur radiatively without locks, and therefore one can imagine that the string scale is a loop factor higher than the electroweak scale, as I will illustrate in an example right away. Moreover, of course, there are new candidates for dark matter, etc., using extra dimensions. Now, since this framework does not rely on unification, which is also you can think that it is a drawback. On the most convenient framework for this are models of d-branes, playing with a volume of the transverse dimensions, which has to be 10 to the 32 in units of the string scale in order to explain the hierarchy. So it needs large volume compactifications. Now, in such a model, in such a framework, the Higgs could come from a locally supersymmetric intersection. Suppose that you start with type 2 string theory, and you have configuration of branes which breaks completely supersymmetry, either by intersections of the branes themselves or by branes with orientifolds. Still, one could, in such a class of models, in order to have a massless scalar, this massless scalar has to come from a supersymmetric intersection. But since the model does not have supersymmetry overall, nothing forbids radiative corrections to develop a mass, and this mass can be computed in any particular model. For instance, I have here an explicit example where this computation can be done using, for simplicity, allowing only one free parameter, which is a compactification radius. And there are two possibilities that the Higgs comes from truncation of a supersymmetric theory, of an extended supersymmetric theory, in which case its self-coupling, although its mass is zero, its self-coupling is given by truncation of a supersymmetric theory, and therefore is given by the same relation as in MSSM, by the D terms. Or another possibility is that this is not valid. This relation is not valid. Then one can visualize how string scale acts as a cutoff, as an effective ultraviolet cutoff, because this is the correction to the one-loop correction to the Higgs mass, which is quadratically divergent in the effective field theory, but in string theory is cut off by the string scale, and this is how how it happens by the insertion of this piece, which contains information about the string oscillators and falls off exponentially in string units in the ultraviolet limit, where L is the length of a singular of the cylinder. Actually, this one loop annulus diagram. On the other hand, in the infrared limit, when L goes to 0, then this insertion goes to 1, and the result can be re-derived by the effective field theory just by taking into account that you have extra excitations, Kaluza-Klein excitations, because the theory is high dimensional. Now, there are two interesting limits. The first is the limit of a decompactification of a transverse dimension to the brane. And this happens, I mean, this parametrization is when R goes to 0, because by T duality, the 1 over R goes to infinity and becomes the transverse dimension. Then its coefficient is computable, cannot be computed in field theory, it can be computed in string theory. The sign depends on the relative weight between fermions and bosons. There are examples in which the sign is negative, and the coefficient is a loop factor suppressed. So that's realizes the idea. The other interesting limit is R goes to infinity. Now, which means infinity means large compared to the string scale. In this case, you have there is an ordinary dimension along the brane that decompactifies, and what happens is that in this limit, the string scale is cancelled and is replaced effectively by the compactification scale, which plays a role in that case of the effective field theory, with a coefficient which is calculable in the effective field theory. The reason for this simplification is because in this particular example, the Higgs scalar is a component of a higher dimensional gauge field, and therefore its coefficient is calculable in the higher dimensional field. So that illustrates this possibility. Now, taking into account now the quartic coupling, there are two possibilities. First of all, in the case where the theory, the quartic coupling is obtained by a supersymmetric truncation of a supersymmetric theory, one obtains a three-level relation, and the Higgs mass is equal to the Z mass. Essentially, is because you have one Higgs and you go to the limit of large tangent beta, and of course this relation will get correction now only from the low energy point of view, only fields only from the top quark. It may get also higher string loop corrections, which are model dependent from the model. Now, from the low energy thresholds would push the Higgs up to 120 GeV because you have only the top and not the stop. But of course, this number will be subject to string threshold corrections, which are model dependent. Another interesting, also at the same time, the string scale or the compactification scale, it's a loop factor higher than this scale, so it can be fewer several TeV. Another interesting limit, let's say, is when the Higgs does not arise from truncation of supersymmetric theory. Then the relation that this relation does not hold anymore, and for instance, by introducing just by replacing this with taking the two couplings essentially to be equal, which is the string coupling, then we can easily get masses of the order of the half of the string wave as a tree-level relation. Okay, now the main prediction of these models are model-independent prediction is missing energy from the gravity emission in the bank, which already has analyzed in LHC and give bounds of the order of 2 to 3.5 TeV, depending how many extra dimensions there are. So the stronger bounds are for 2 extra dimensions, the weaker bounds for 6. One can ask, the next question is what other predictions you can one can have, because the previous one is actually a prediction of strong gravity but does not probe really the string theory. One can think of black holes. Unfortunately, in this framework, the string coupling is small because it's perturbative, and the black hole mass is 2 orders of magnitude higher than a string scale. So this is out of, it's not relevant for LHC, at least, if the string scale is low. The other possible predictions have to do with 3 different scales that these theories possess, and can give rise precisely to particles with masses which are associated to 3 scales. The first are string oscillations, which are really probe the string character of the theory, in the same way that in gauge theories, the real test of gauge theories would be the discovery of W bosons, of gauge bosons. For a string theory would be the string excitations, but of course for this one has to be very lucky to discover. There have been analysis from Munich and Northeastern group, where the main their main result is that since the theory is perturbative and these excitations are open string excitations, there are model-independent predictions for this production of string states, which do not depend on the compactification details. And the present LHC bounces is 4 TeV using this analysis. The second type of predictions are extra dimension TeV dimensions, are associated to the brains, seen by gauge interactions. And for this, the experimental limits vary between half a TeV and 4 TeV, depending on how matter fields are localized in this space of extra dimensions. So in the case that, in the extreme case that none of the quark and leptons are localized, it's universally, let's say, universally in the bulk, then the limits are weaker. And in the other case, where everything is localized, is 4. And in general, depending on the model, the limits can vary between the 2 numbers. The other possible scale that exists are scales with U of anomalous U1s. We had already such talks. Thank you. If a U1, this theory with intersecting brains have, in principle, extra U1s. These U1s are in general anomalies, and since the anomalies are cancelled by the Green-Schwarz term, the masses are suppressed by a loop factor from the string scale, and therefore even if the string scale is higher than the LHC reads, such an anomalous U1 could be reachable. Now, these U1s usually gauge non-global symmetries of the standard model, which can be anomalous or not, such as combinations of the baryon number, lepton number, or Pet-Sequin symmetries. And in principle, there are 2 types of massive U1s that one can get. U1s which are which have four-dimensional anomalies, and these masses is directly related to the anomaly times, well, times the string scale, of course. It's a loop factor. But the second category of UANs are even UANs that are not anomalous in 4 dimensions. Still, this does not guarantee that they remain massless, because still there can be they can receive masses of the order of a string scale related to 6-dimensional anomalies. And 6-dimensional anomalies have an extra torus. Comparing these in the general situation, comparing these two type of masses, these are heavier than these ones. One could imagine a situation which is opposite, but that's the generic situation for these models. Now, that is a model that has been shown a few times in this conference, which I guess it was first by the Spanish group that they constructed, but it was also constructed by the group of Selikens in using superconformal blocks, and it has a U3 for the with an additional U1, which is a baryon number, which describes the strong interactions. It has a U2 that can become an SP1 if you put if one puts the orientifold plane here to get rid of the extra U1 to describe quick interactions, and then it has two additional branes. One is the lepton number, and the other is the U1 right. So there are three extra U1s, three U1s, sorry, and a combination of them is a hypercharge, and the two additional U1s are actually the baryon and lepton number. Now this is a typical thing that you need in these constructions, because you need baryon symmetry to protect the proton decay at low energies, and you need the lepton number to protect small neutrino masses from dimension of 5 operators that could generate Majorana neutrino masses. The plane with these two U1s, in this case, there is one which is anomaly free, which is essentially the B minus L, and this, depending on the model, could have 6-dimensional anomalies, and therefore it could become massive. It could both of them could become massive. This one, being anomaly free, would be heavier than the other one, and the other one is just a baryon number, essentially the Z prime with a baryon number, and this could leave, of course, interesting experimental signals, because it has leptophobic couplings. One could imagine the same model, just take it the string scale. This work we did recently, from the TV to Planck scale or to grand unification scale. Then in that case, the Z prime, which is essentially the baryon number, which is the anomalous one, the 4-dimensional associated with the 4-dimensional anomalies become super heavy, because now the string scale is very high. And one can, on the other hand, the B minus the other combination, which is essentially the B minus L, could be arranged to be to have no associated 6-dimensional anomaly, and therefore to keep it massless at the string scale and break it at low energies by introducing an expectation value of the Higgs, of an additional Higgs, which has the quantum numbers of the right neutrino. This has this is a model, an interesting model that can be analyzed also. The lepton number violation from higher dimensional operators is suppressed by the string scale, so that's a nice property. And the present LHC bounds for such Z prime, which now in this notation is Z double prime, is bigger than 2.5 TeV. And they have interest in phenomenology, LHC, and also cosmology. So let me say a few words. The point is that so it starts in the beginning with BL and U1 right. The couplings are there are relations amongst the couplings that one knows, and then one does a rotation to the, from this string basis to a low energy basis, which contains a hypercharge. Then in this basis there is one anomalous U1, which is I call Y prime, and which will be decoupled at low energies, and then what is left over is a linear combination of the hypercharged and the B minus L. Now, playing with the couplings and requiring that the theory is perturbative up to the string scale, one finds that the leftover linear combination is actually mostly B minus L. By mostly means 90% or more, and the LHC discovery potential for such gauge bosons are up to 5 TeV approximately in the DiZ channel. Now, what is interesting is that this model contains containing additional right-hand neutrinos, and one could try to use them in order to accommodate the recent cosmological observations of an extra relativistic component of the universe, which is dark radiation, that Redondo talked about the first day, which suggests that the effective neutrino number is close to 4. Now, since so one could use these 3 right-hand neutrinos that interact with the standard model fermions via this Z double prime, and observe that their decoupling has to occur during the quark-hadron transition for low masses of Z double prime, which means that they are not completely reheated, and therefore they can play a role and can account for this number. So by doing the exercise and fitting these extra right-hand neutrinos as an effective additional neutrino species, one can one can find the regions of the masses of the corresponding allowed masses for this Z double prime, and one finds that there are 2 possibilities: either that have equilibrium in the absence of a chemical potential if the annihilation channel is decoupled, or the usual thermal equilibrium. And then one finds a region in which, in principle, is testable in the LHC, the second one. How much time? 1 minute. Okay. Then I mean the other thing that I wanted to mention is another possible realization of effectively of low string cutoff by using not a number of Kaluza-Klein modes as a effective number of species, or to lower the string scale, viewed in this picture with large extra dimensions, essentially give you the large number of Kaluza-Klein modes for the graviton, but use the effective number of string modes in order to lower the string scale. Then one finds that in this case one could lower the string scale by playing with a string coupling, by introducing a string coupling which is very, very small, 10 to the minus 16. And of course, this does not work in deep brains, because in deep brains the gauge coupling is related to the string, proportional to the string coupling. But one could, this framework could work when one embeds the standard model on NS5 brains, on NS45 brains. There is a simple, one could use ADS-CFT to describe these models, and essentially one can pin down to a toy model, a 5-dimensional model which captures this picture, which it's essentially dilaton gravity in 5 dimensions. This has 2 solutions. One solution is constant dilaton and with a cosmological constant, which is a dilaton potential. One solution is constant dilaton and ADS background, and this essentially produces the Randall-Sundrum models. We'll stop. And the second solution is a linear dilaton background and flat sigma model metric, and that can realize this, essentially can describe this background, this new background. So this gives another simple realization that extrapolates between the flat and warp extra dimensions, in which the graviton, there is a graviton zero mode which is flat between the 2 branes, and the Kaluza-Klein gravitas are localized near the standard model brane, which is now near the origin. So one gets this typical spectrum of Kaluza-Klein modes, where it's effectively like one has an extra dimension, one extra dimension, but with a mass gap characterized by this alpha, where the mass gap is essentially related to the coefficient of the linear dilaton. So one, by playing with this parameter, one can extrapolate between a pixel which looks like Randall-Sundrum and a pixel which looks like flat extra dimensions with one extra dimension. So just to conclude, going back, the possible discovery of the Higgs scalar DLHC I think will be a big step forward. One will need precise measurement of its couplings, and this could give a hint of the answer or not to the mass hierarchy problem. Would like to answer if there is supersymmetry in a natural or unnatural way, or if there is no such supersymmetry, if there is something else, like for instance low-scale string in some realization. And personally, I believe that there is a good chance that in the next phase of LHC will provide the answer if in this phase at least the Higgs is discovered. Thank you.
Are there any questions?
I was confused by the statement that the Z prime that's in the bulk is heavier than the one that's localized.
Sorry, the Z prime is?
That the one that doesn't have anomalies in 4 dimensions is heavier than the one that does. How does that happen exactly? Because I would think that would be the other way around. So.
No. The reason is you have to think in terms of localization. That if you have 4-dimensional anomalies, then these anomalies are localized in 6 dimensions, and therefore the where is it? Sorry. Where is the mass? Yeah, and then you obtain these relays, okay, where Z is a string couple, is a string couple essentially, which is related to the coupling of the anomalies U1.
Yeah. The confusion
in the
is
case,
the other one.
in the other one, what
That's
happens
not volume
is that
suppressed, but it's volume
the anomalies are now localized in 6 dimensions. Okay, so it is true that if you think in terms of the string coupling, you will have the suppression of the volume. But if you translate it into the coupling of the anomaly of this U1, then there is the volume which appears here. Okay, so that's it.
No more questions. Let's thank Antoniadis again.